Yes, I hope you can see what I'm displaying. It's the same document I was looking at yesterday. I didn't send this to you because it's basically just a blow up of the course description which I sent you, but also because especially this particular area of um, of the course, this particular third, um, which was our choice, we we are not going to cover the entire. We're not going to cover all the areas. Uh, so I picked the areas more which are more to do with the um, which help you understand how to do analysis, performance analysis. Because we will not even do the performance analysis, but the areas we we will cover will help you do the performance analysis. We'll be looking at the various issues that actually hinder performance. Yeah, but to understand that, sorry, I think I was advised I can invite you in different ways so that I don't keep on admitting. I don't, we don't keep on having these breaks while admitting people. From the next class, that's what we're going to do. So we say that we are going to look at the layered models for a start. Uh, Somebody said that you did it in high school, so we will look at it probably in a bit deeper, because only then can we be in a position to do what this section is asking us to do. So we will look at the layered models. We look at the two most popular layered networking models. That is the OSI model by ISO. Um, Sorry about the verbs. Yeah, by ISO, and the internet model, which we also call the TCP/IP model, uh, which is the model on which the almost all our communication systems are based on. Uh, Nonetheless, OSI model is very popular. It's used for teaching because the whole idea of the model was first of all to break down. Is layered. Break down is uh, the model into manageable layers. So, and I think the more layers you have, the simpler, uh, or rather, it reduces the complexity better. So I think maybe that's why we use it for teaching, because it's a 7-layer model, and this other internet model is a 4-layer model. So actually, although it's not what is being applied, it actually breaks down the layers in a better way, and make them simpler to understand. That's what you're going to find out today, in spite of using the TCP/IP model. Whenever we describe networks, we normally use uh, the, the, uh, the, the ISO OSI model uh, layers. So we talk about layer from layer 1 to 7, uh, which are actually the layers of the OSI model. So we'll look at that. We are going to look at data link layer protocols, flow control, uh, uh, Flow control is just one of the things that happen in the layer protocol, but flow control is one of the issues that um, implemented, or rather one of the systems implemented in a computer network to try to improve the performance of a network. Yeah. So we are going to look at that in details, the flow control methods. Uh, we'll look at IP, but for the IP, we will not get into IP addressing. That's why I put this part, that's why I cancelled this part, network addressing and routing. Yeah, it's another, actually these are two different large topic. Okay, routing is here. These are big, large topics in, in computer communication. We'll look at routing, would like to, but for the time we'll be having, we'll not be able to look at routing. And I hope you have come across routing, but I just mention it. But we won't get into routing techniques in details. Protocol design, message formatting, and encapsulation. That we are going to do it. The models we are going to look at. We will look at encapsulation and message formatting as a concept. We will get into protocol design uh, uh, as an exercise because we again time is a constraint, and also the requirement of this course, of course, does not call for details uh, in this area. Network security and privacy, again, we will look at that area. That's issues with cryptography and uh, authentication and all that. We'll look at that. But we are generally going to deal with areas that, as I said, would assist you in performance analysis because that's what the syllabus asks us to do. So that will be exactly what we are going to cover in the 12 weeks. And in a nutshell, the course is divided into three parts: information theory, error control coding, and now uh, computer communication. It's much shorter than FEE521, so we will not need to rush. Uh, and I've seen maybe we didn't even have to rush. I got I got your course outline for FEE52 and 421 and 422, and I found that in 421 you have covered a lot. Uh, the background because we were to do FFT, but we went to the background of DFT, which I found we had already covered. So probably that's what is making it a bit longer. Uh, but I found that you have actually covered very many, a lot of communication in 421. I think 422 you mainly covered the pulse modulation, the the the, the various pulse modulation techniques. I saw there's a large part of electroacoustics in 422. But that one is not very concerning as we are more looking at the communication side. So we'll start. If there are no questions on what we are going to cover, I think we can look, we can start, we can go to information theory and source coding. I hope you are able to, you managed to download Shannon's mathematical theory of communication. I think that's what the paper is called. Yeah, a mathematical theory of communication. Yeah, I said 1960, I think it's 1948. That's when Shannon produced this paper. And if you read the paper, the things it brings out is uh, what today we take for granted. But in 1948, that is shortly after the war, that must have been a big thing. Yeah. But what um, I think what really Shannon gave us is sorry about my camera seems to be frozen. The camera is frozen. I think it's okay since you can hear me. So I mean, what they give us is the ability to predict the theoretical limits of uh, that is on the channel, the theoretical limits, of the capacity limits of the channel, uh, based on probabilities. Yeah, on the probabilities of receiving various symbols. Yeah, because in Shannon's model, data had to be encoded. It was not talking about the analog information. It was only when data is encoded. So it's talking about digital communication. Yeah, yeah, where data is encoded before transmission. That's why the information theory basically deals more with deals actually with uh, deals with encoded data. We are trying to extend the same theory to analog communications, uh, analog transmission. Uh, you could see from the course outline, but basically Shannon uh, arguments or findings were based on transmissions that were uh, encoded, or rather, which have gone through the process converting from analog to digital is something we have discussed. I mean, I saw you have covered in your course. Yeah, the process from sampling, quantization, and then eventually coding. Yeah. According to Shannon, some of uh, the issues Shannon was looking at is that fundamental problem of communication. And we call it the problem of communication because that's what any communication system tries to do. That you are sending a symbol, uh, or rather, what represents. When I refer to a symbol, I'm referring to what represents the data, the zeros and ones, some physical entity, yeah, which we looked at last semester under modulation. There is a physical entity which you are transmitting to carry the data. Is voltage, change of voltage, change of phase. Uh, so the whole idea was you should be able to select that message. You should be able to get the message that was sent. Yeah, because whatever message was sent will be a symbol from a certain group of symbols. And so you have to select at the other end, you have to know which symbol it was as accurately as possible. So those are the issues channel nodes are dealing with. And what we mean by symbols, we mean, for example, if you are carrying zeros and ones, so the symbols will be either, if you're using, if we are using, let's say, the symbol, of course, will depend on the signaling scheme you're using. By signaling here, I mean uh, the conversion of data into a signal. So if it is, for example, PSK, one symbol could be zero phase change. So zero could be zero phase change. Yeah. So this is a phase. And one going to be pi. Yeah. If you are carrying, let's say, if you are using carrying 2 bits per symbol, this would be 45. This is 135, 215. I think we looked at it. And this should be 215. No, I think 225 and 315. So these are the symbols we are saying. So the choices, one of these symbol is sent. Yeah. And your network, the receiver should be able to, as accurate as possible, identify which symbol was sent. I think the next point, of course, is what I've already mentioned, that the messages have meaning. That is, they refer or are coordinated according to some system with certain physical or conceptual entities. Yeah, so messages have meaning. So they are in the communication system. They will be related to some certain physical uh, entities. I think this I've already said. The second aspect is that the actual message is one selected from a set of possible messages. And this was my take. I looked through the paper and mainly this was my take. But it's good that you read the paper uh, because most of what you have to do is based on the findings of Shannon. I think it's about a 50-page. I hope I'm right. It's about a 50-page document. The system must be designed for each possible selection, not just the one that will be chosen since it is unknown at the time of the. So your system must be designed uh, to carry any of the possible messages. Yeah, because it's not known at the time of the design. So it can be, when you design a system, you also design that it can carry uh, any of the messages. It will depend on the type of modulation, type of encoding. But you're saying the system, you can look at it from the group of symbols, but I think it is talking more on the possibility of using different symbols to carry your data. So that must be taken care of in the design. So that break and the number of messages is finite. This number can be regarded as a measure of the information produced when one message is chosen from the set, all choices being equally likely. I think we are going to look at this in details. Actually, this will be one of the pieces of our discussion. Uh, it's talking about the concept of information based on the probability uh, of getting a certain message. Yeah. So we'll be dealing with the numbers, which you are going to call information, and that will depend for each symbol on the probability of uh, probability of a symbol being transmitted. Because as we in the alphabet, all symbols are not don't have the same probability. Yeah. So we are talking about in this case all choices being equal likely. The symbols are not equal likely in practical communication. Uh, for example, A, the vowels are likely to appear much more than the consonants. Yeah. First is because they are few, but almost all almost in all languages, you find that a sentence will have, I mean, a word of let's say 5 letters or would have at least maybe two a third would be would be vowels. So the message carried by those symbols actually depends on the probability of their occurrence in the text. Then the last one is talk about logarithmic measure, why we use logarithmic measure in when dealing with information. At that time, I think it was since we are dealing with digital. The example used here is the relay, uh, because it has either on or off position. It is very similar to the choice of zeros and ones. And the argument was that for adding one relay, it gives us doubles the number of possible states of the relay. And that's what actually happens in communication. Adding one bit doubles the number of possible positions. Because adding one means you're multiplying by 2 into the power 1. And we know that we see that if you have got 2 bits and if you want to carry 2 bits at a particular time with a signal, with a symbol, then you need 4 symbols because there are 4 different states. If you add a bit so that you want to be carrying 3 bits per symbol, then you have to double that figure, it becomes 8. And of course, today it looks straightforward, but uh, I'm sure when Shannon came up with this, it was uh, it was something big, huge. Yeah. So yeah, this paper is good to read. Go and read it. It's a long paper. I said to reduce it to about a paragraph. Uh, I may even have missed some critical issues from the paper, but that's what I picked from that paper, and I looked at it. And I thought probably that's what it, at least it gives us some good insight uh, into what we are going to deal with. So Shannon came up with this model, which again today we take for granted. Yeah. Uh, Nowadays, I mean, if you looked at the model, which we looked at the digital communication system, which I introduced, uh, which I showed yesterday on FE522. It's based on this. It was only that it was a bit more detailed. We give out the satellite transmission, yeah, apart from the modulation for the digital communication and channel communication model was based on the communication. Yeah, as I said, although we try to use it for the analog communication, it was mainly based on uh, the digital communication. In that case, you have things like error control coding, you have source coding inside here. Of course, you have the noise. Yes, noise. So you have to model noise also. There are many possible sources of noise without, both within and without the communication system. Uh, Interference from other sources, interference from other communication sources, and also from other sources like lightning, machines being operated near the system. Uh, but there's also the internal sources like the Johnson's noise from thermal noise, you know. But with all that, with when you combine all those sources, it was found that basically you can model the noise as white noise. So that's why and also it was discovered that it's also the distribution is also Gaussian. Yeah, that's why up to today we talk about the AWGN noise. Yeah, the additive uh, white Gaussian white. So information source produces a message or sequence of messages. Yeah, see the message or sequence of messages to be communicated to the receiving terminal. So the message will be a sequence of letters as in a teletype system or a function of time as in radio or telephony. Yeah. So it may be any of these, but of course, as we said, uh, Shannon's findings can be extended to the analog system, um, but it's a bit complicated to apply that because you have to assume that system has been uh, uh, digitized. Yeah. Uh, then of course the transmitter, that is the source, the transmitter. Well, those are things we know, but it's still good to. The transmitter operates in some way to produce a signal suitable for transmission over the channel. What we are saying is exactly what we normally try to do to the signal before we send it to the channel. The suitability here, we are talking about many things. One, in any communication system, we try to, I mentioned before, we try to carry as much data as possible with as little um, with as little as with as little bandwidth. Well, that's not it was bandwidth is how much you carry. We try to carry as many uh, bits as possible, as much information as possible. Sorry, putting it that way, as much information as possible using the channel as little as possible of the channel. Maybe that's the best way to put it. So one of the things we try to do is try to carry information with the least number of bits possible. Yeah. So if we find we don't have to carry certain data and still we are able to communicate, then we call that data redundant and we remove it. And basically, that's what you call compression. You know, you are removing what you don't require. It's redundant because you want to carry as much information. At the end of the day, it's not the number of bits you carry; it's how much information you carry with those bits. Yeah, because we start with information, then we go to the bits, and then we go to the signal, which you eventually transmit. But even before you transmit that signal, you try to get rid of any redundancy. So when you say we want to make the message suitable for the channel, one thing we're talking about is compressing it where possible. Removing any redundancy is possible. And unfortunately, with the same process, we still find ourselves now having to add redundancy, yeah, for error detection and correction. And with detection, you add certain amount of redundancy to be able to detect the errors. For correction, you add much more redundancy to be able to to correct the errors. So generally, if we have a channel which we suspect, uh, or rather, we have information that, or we know is our channel, we have created it. We know our signal is not going to encounter a lot of noise. For example, when you transmit data over a cable and a short cable at that, probably when you design your system, you may not include error correction because error correction takes a lot of overhead. Yeah? So you may only employ error detection methods. Yeah, because so that once the packet is found to have errors, you ask the transmitter to retransmit, and when you do your overall maths, you find that once in a while asking the transmitter to transmit actually is more efficient than including all that overhead and then there are no errors. You get it? Because the theory makes sense when there's a lot of errors that you have added out of redundancy. If you done all that redundancy and then there are no errors, it becomes a total waste. Yeah. I was looking for a suitable example to give in real life. Uh, and actually it happens, especially in things like switching. With switches. So we have a system whereby a switch is designed such that it can be able to look at the packets and find out whether the packet have errors, and if they have errors, they drop the packet instead of transmitting it. Yeah. But we also have switches that don't read. Actually, one of the operating which don't read the packet. They just get the packet and forward it. So when you are designing a system, you have to know your system. Do I need a switch that only works in what we call cut through mode? Cut through mode. You don't you don't store you don't store the packet. We call it storing because you must store it temporarily to be able to look through it and then forward it. We call it store and forward. So do you when you're designing your system, you have to know that the system I'm using It's not likely to have uh, noise, because noise is a major source of errors. Yeah, if a channel is noiseless, as we are going to see as we are going on, if a channel is noiseless, the likely it's going to be lossless. It can be lossless when it's noisy, depending on the amount of noise. But for it to, when it's noiseless, then it's lossless. Yeah. So that's what we mean by producing a signal suitable for the transmission over the channel. So I think there's a, for example, in telegraphy, there's an encoding operation produces a sequence of dots, dashes, and spaces. Actually, these are the precursor to the zeros and ones. This is was the original digital communication where you're sending dots and dashes, mark and space. In a PCM system, speech must be sampled, compressed, yeah, quantized, and encoded. Okay, that is not exactly the order. The order is sampled, quantized, encoded, and probably compressed. If you can remove, you can use various methods to compress. Various methods that will remove, uh, will remove redundant data. And sometimes not removing. Sometimes it might just be a different way of representing the data. Yeah. For example, suppose you have got a one, and then you have. I just want to introduce that concept because it's actually one of the compression methods. Yeah. I think it's called run length encoding. Yeah. Because suppose you have got a one, and then all these zeros. How many zeros are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Ah, no, actually 15. It might actually be easier just to write 1 followed by 15 zeros. So you carry the information 15 zeros. So you can you can have 15 zeros, you can have 15 in hex. Yeah, it is likely to take less communication space. Yeah, because if you're sending a hex of 15, it simply, I think, should be one. I don't know. I think 15 should be what? That is 8. Oh, 15 is actually all ones. Yeah, 15 zeros. That is all ones. Yeah. So that can be a way of compressing. It may not be necessarily that you're removing, but you're just representing the information in a different way. Yeah. But we are going to concentrate on the compression, uh, which you can achieve through coding based on the information carried by the symbol. Yeah. The channel is the medium used to transmit the signal from transmitter to receiver. These are the possible chases. It could be a pair of wires. Uh, the pair of wires we normally use is twisted pair. Can somebody tell us why the pairs are twisted? I don't know what's with my screen today. I'm not able to see. Let me change the layout to see more people. can see why I was not seeing anybody. I'm out of luck. I can't see. But can someone tell us? I'm trying to see individual names. I can't see, something is wrong with my screen.
To prevent crosstalk.
Yeah, that is the main reason, is to prevent crosstalk. Yeah. Uh, you prevent crosstalk. You also, you actually reduce interference. Of course, crosstalk is one of them, but also interference from other sources, even external to that particular cable, because of that twisting. So the fields induce current in different directions when you do. I think it comes from the original transposition, which of the overhead wires, because most of the communication we used to have, our telephone used to be through overhead wires, and they were bare. They were not coated. And what you find with the power lines, that's how our telephone lines used to be. Yeah, for a long, long time. This wire PVC is a very new concept. Uh, well, it's not that new, but especially for long range transmission. So there used to be the transposition, and that same concept was uh, taken to these twisted pairs. So the pair of wires we are talking about is the twisted pairs. It can be the coaxial, um, which we don't use much nowadays. We use twisted pairs a lot because the capacity of twisted pairs has been going up and up. I think now we can be able to do up to 10G. Uh, I think on category cat 8. Yeah, for those who may have uh, a chance to come across networking hardware. Not be aware now, I think we're in cat 8, and then with cat 8 cable, you can be able to carry up to 10G, up to about 30 meters. Yeah. Um, so we don't use coaxial cable anymore in networking. Of course, we still use it to transmit signals from maybe the antenna, the outdoor antenna, to maybe your indoor, uh, your indoor receiver or transmitter. I mean the unit which is indoor. Yeah. So the receiver performs the inverse. I think we know that, done by the transmitter. That is reconstructing a message from the signal. Because what is actually transmitted is a signal, but you try to get back your message, the original message that was carried by the signal. Because that's the whole idea of a communication system, is to get what you transmitted as accurately as possible. And of course, the destination is the user who the message is intended. Yeah. So, as I said, today is what I've been talking about is something we take for granted. Um, but I believe it was huge. Any questions so far on that introduction before we go to the nature of information? So, Let's measure of information. IT, what we are looking at, provides a quantitative measure of information contained in a message signal and lets us determine the capacity of communication channel to transmit information from source to destination. We are saying actually the capacity of a channel is actually based on this measure of information. And if you are given a discrete source, so note we are using a discrete source, and in this case will be the source will be dealing with is a memorized source where the current output only depends on the current input. Yeah. So we are going to look at the memory source, and we are saying for a discrete source, which in our case will be a memory source, with n possible outcomes. You have n possible outcomes. It means you have n possible messages. And we are saying j goes from 1 to n. Yeah, that's what we mean here. We have n possible outcomes. That is, the j is going from 1 to n. The information associated with the j's message is given by this equation. When you transmit the jth message, it's given by this equation. What it means, the information of that particular symbol or carried by that particular symbol is equal to log 2 1 over pj, where this is the probability of that message being carried, or rather being the message which has been carried is that message. Yeah. And the best way to see it is if you have a long message, and again I think I'll use like using this abracadabra. I like that abracadabra because I know how many E's I have. I always give that example, abracadabra. Abracadabra. To give you the idea, we are saying A, I think I gave you this example. I give it too many times, I don't remember where I gave it to. So A is 5, I think B's are 2, C is 1, D abracadabra, D is 1, cabra, R is 2. Yeah. So these are 11. What we are saying is A, judging only from this name, of course, doesn't mean this is a sample of your passage. I'm only judging from this particular word. Otherwise, in a passage, you have to get the average of the entire passage. But I'm saying if you assume that where this came from, that ratio is maintained, or you are making words with only these five symbols, A, B, C, D, and R. Or rather, A, B, C, D, R is your alphabet. We call that the alphabet. The English alphabet is A to Z. So we're just assuming we have a new alphabet that goes from A to R. So whatever you're going to write is going to use this and is going to have the same ratios We know it doesn't happen, but I'm saying suppose we do that. What we are saying is A appears more times, so it has a higher probability. Yeah, it has a higher probability of occurrence. Its probability is 5 out of 11. Yeah, and we are saying the information it carries is inversely proportional to its probability of occurrence, or is proportional to the log of. So it's actually not directly inversely proportional, but there's a log thing here. But we can see, and it makes sense that information which is rare, uh, or rather, I'm trying to say the best occurrences which are rare. Actually, the, the, they are considered to be news because intuitively, I mean, just intuition, they are considered to be news because they carry more information than the ones that happen every day. If you tell somebody obvious, most likely you will not be interested. Yeah, because there's no information in what you're saying because it has been said so many times. But when you say something that has not been said, somebody listens because there is information in what you're saying. Yeah, and uh, that is a concept based on which we we are able, even the formulas we know today for capacity are actually based on these concepts. Yeah. So I of j is equal to log of 2 1 over pj uh, bits. Or rather, I of j is just negative log 2 pj. Yeah. It should be the same as just putting negative log 2 of pj. Where I of j is the information carried by the j symbol. Pj is the probability of occurrence of the j symbol. So symbols with a higher of probability of occurrence carry less information. So that is the definition of information. And then we introduce the concept of entropy or average information. Yeah. And entropy, and we are going to show that. I think this thing we are going to show just um, below here. And whenever you talk of the entropy, we are talking about the entropy of a source. Yeah. Entropy is associated with a discrete source. A discrete source is something like your keyboard. A keyboard is a discrete source, yeah, which it produces discrete symbols. Yeah, when you press a D, that's a discrete symbol. So if your keyboard, well, keyboard has so many things, so it has very many symbols. Yeah, but for our calculation, we'll be using fewer symbols. You'll be given symbols, and then we work out. We will be given symbols and their probabilities, and then we work out the entropy. So the entropy over discrete source S denoted that is the symbol for H for entropy. You normally use H and then you use capital because we are dealing with probability. So we like using capitals for things which are expectation when you're dealing with expectation. Is the average amount of information associated with that source. Yeah. Sorry, somebody's coming in. So Yeah, it's so the entropy is associated with a source. So whenever you hear about an entropy, then you're talking about a source. So H of x is the expectation of I of xj. So what we are saying here is the expectation, and whenever you talk of expectation, by definition, or that will be the expectation, it will be its probability, because that gives us a distribution, and times I of xj. Yeah. So that is a summation of pxi ixj, and this can be given by, of course, you replace the uh, ixj, the pxj. Yeah, you can replace this from this definition here, which is simply ixj is minus log 2 pxj. So that's what we are saying here. So we are saying entropy is simply negative uh, uh, j, j is equal to 1 to m pxj log 2. And of course, you can see how we are getting from expectation to this to that. We are simply replacing ixj with uh, the log of pxj, and that's negative. So that is the entropy, where m, of course, m is the number of possible outcomes. So m gives you the total symbols. For the alphabet, the symbols are 26, but of course there are other, I think the other symbols are associated with the alphabets. Is that the Latin? No, that's not the Latin alphabet. The alphabet which you use, of course, there are many other symbols, commas, full stops, uh, capital letters, small letters. So there are more than 26. Yeah, but what you mean m is a number, is a size. We call it the size of the alphabet. So you have got S1, Sn. So n is the size of the alphabet. You have S1, S2 to Sn. M is the size of the alphabet. So that is the definition of entropy. And Pj is the probability of the jth message. So I hope we are together so far with the concept of information. Yeah. And we have seen that it makes sense in everyday life, that less is more. That's why also people who don't talk a lot, when they talk, you listen. Yeah. Unfortunately, as lecturers have to talk a lot. That's our profession. Yeah. So as much as we agree less is more, I think we have no choice. We have to talk. That's how that's how we deliver what our mandate. So the source entropy Hx satisfies this equation. We are saying Hx will never be greater than log 2m. Yeah. So if you have got H symbols, it means the entropy will be log 2 of H to be 3. Yeah. And this is very important to know, because sometimes you may have calculations on entropy, as we are going to have. And If you calculate entropy and you have got 8 symbols and your entropy comes to 4.5, then you know your answer is wrong. You get 3.1, you know the answer is wrong. The entropy should always be less or equal to log 2 of the number of symbols, the size of the alphabets. Yeah, that is important because we'll be doing calculations on this. So it's good that when you do your calculation and you find the figure of your entropy is more than log 2m, redo the calculations. Yeah, something has gone wrong somewhere. And here we are deriving the entropy of a discrete source. So we are saying consider a source that generates m different symbols, x1 to xm. Yeah, with the probabilities px1 to pxm. Yeah, say n symbols are generated over a long period. Yeah, this makes sense. You have got m possible symbols, but they are generated over a long time, a long interval n, which is much bigger than this number. So it means if you have got, for example, m is 8, yeah, you're not talking of just 8 symbols. You are talking of maybe a passage. So some symbols will be repeated, yeah, because if you have only 8, some may not even appear. Yeah, so if n is equal to 8, some symbols may not appear. Yeah, so we are saying suppose n is much greater than m. Yeah, then we can say the number of x1 symbols is px1n. Yeah, that is what probability is. It will simply be the probability times the total number of symbols. Yeah, because that's what we did with abracadabra when you said the probability of A is 5 over 11. It is because the probability of 5 was 5 over 11 times 11, which is the number of symbols is 5. Yeah, amount of information in each symbol, x1 symbol, in each is this by definition. So in x1 symbols is px1. The amount of information, I think I've left something. Oh yeah, that's okay. Because this is the number of symbols generated. Yeah, the number of symbols generated, and in each is this. So you're simply multiplying this with this. Yeah. So the number of symbols are that, and each symbol carries that. So you multiply this. So the total amount of information in all symbols, IT. Yeah. IT is px1 n log 2 1 over px1 plus px2. That's this probability of symbol x2 times the information carried by each of those symbols x2, and you go that way up to p of xm and log 2 1 over p of xm. So we are saying that is the total information. That information is carried by each of that symbol. Yeah. So the average information is simply that total information divided by n. So if you divide by n, then h of x is p of x1 log 2 1 over p of x1 plus all that and that can be written as this. Of course, it is plus 1 over pxi, or just minus log 2 px j. Yeah. So I think that is clear. So we are trying to derive, we are showing that actually that is a formula for entropy. Any question? Any question? I've been talking. It's an opportunity for you to ask question if you didn't understand. If it is clear, that's good. So the other thing we are going to look at is the information rate, R. An information rate is given by the symbol rate times the entropy. Symbol rate times the entropy, where R is the rate at which the source emits symbols. So we call the symbol rate times the entropy. That's the information rate. We're going to see more about. So now let's look at types. We look at the discrete memory source and how discrete memory sources are characterized, and then we also look at the different types of discrete memory source. Okay. There is this memory source. Sorry about that. I think here we so we don't get mixed up. We have a discrete memory source, but now we are also talking about a discrete memory channel. Yeah. So we are going to look at both. So we have been talking about this memory source, but now we are looking at the channel itself, not just a source. Because we have, those are two different terms, a discrete memory source and a discrete memory channel. So a discrete memory channel is a statistical model with an input X and output Y, where input and output are finite and the current output depends only on the current input and not any of the previous inputs. Actually, when I divided the whole, I think I defined this. Otherwise, with the source, is that the current symbol does not depend on any way the previous symbol. Yeah, I talked about inputs. So sorry about that, because the source, we call it a DMS. The current symbol does not depend on in any way with the previous source. In fact, from this we can see that a keyboard emitting our alphabets, I think our alphabets are Latin, eh? They're Latin alphabets, I believe. Yeah. It's not really a DMS. Because when Q depends on what was there before. So I mean, like U will depend on what was there before. If there's a Q, what's likely to follow is a U. So basically, it will not be a pure DMS. Yeah. Because whatever is being emitted, that actually depends on what was emitted earlier. But our model assumes a DMS. But now what we are going to look at is the DMCs. Yeah. This is memory channels. And a DMS can be represented this way by these are called translational probabilities. uh, Translational probabilities P yj x of I. Yeah. So it means here it is this y. I mean x goes from I to m, and y goes from I mean j goes from 1 to m, I goes from 1 to m, and j goes from 1 to n. So we are saying we can fully characterize a DMC with this channel matrix, which we call a matrix of transitional probabilities. Yeah, that is P y given x is P y1 x of 1. I mean, given x of 1, P y2 given x of 1. Uh, so this is uh, these are the transitional probabilities. Yeah, we call it transitional because we are talking about the output, an output symbol given a certain input symbol. Yeah. So if you have, because sometimes you may not have the same number of symbols at the output, coinciding with the number of symbols in the input. Yeah. There may be less or more, and we are going to see those cases where they are less, and I think they are more. But what we are saying is that that matrix transitional probability gives you all those, is a matrix of all those conditions. Y1, so here is x1, x2 to xm, and there is y1, y2, yn. So we are saying the first one is the probability of getting this given that this was transmitted. Yeah. This one, probability of getting this given this was transmitted. So all this is the probability of getting the first row here, is the probability of getting this given that this was transmitted. Yeah. Because there's a probability, because ideally, if it's a noiseless channel, M should be equal to M. Yeah. And when X1 is transmitted, only one Y should be the output. Yeah. But we know that's not the case. Sometimes you may have uh, some probabilities. You may have maybe 80% or 0.8 is Y1, but there's also a 0.2 chance that the symbol will be Y2. Yeah. Yeah. So this is a very important matrix because it is able, we are able to predict the output given the inputs. Although ours is we want to know that to be sure that when I get this output, that was the input, and that's what a noiseless channel gives you. Yeah, a lossless channel also gives you that, although it is not noiseless. Yeah, because we are going to see. Okay, so let's look at the different type of channels. I think I'll give you more detailed notes, but I think I didn't post it. Next time I'll give you more detailed notes on this. I think this is the first one I prepared. So a lossless channel is described by a channel matrix with only one and zero element in each channel. Yeah, this one, maybe I'll give an example. The example which is actually is a textbook example. I think this is the example which is given in. If you look I think I recommended one of the books as what do you call it? I think I have it here. Let's see. Let me see whether I have it here. You can have it with me. You can see something different, eh? Where is this? This book covers this information theory quite well. I think all my mini is based on this. This book is free on the net. Download it. It will help you a lot. And I also like his approach because he gives you examples. Can you see what I'm displaying? Analog and okay, very good. You can. Thank you very much. So this is the book. I'm thinking instead of even. Mhm. Okay, that would be the second page. Ah, this one. Actually, this is a channel matrix. This I thought instead of having to draw it, this will be a lossless channel. Yeah, this is what you are saying. You are saying that there is only one one probability in each column. I think that's what our description is. Let's see. One non-zero element in each column. So that is the one non-zero element in each column. Yeah. Because in this case, we have got 3 input symbols, but 5 output symbols. Yeah. So we have x1. So when the input is x1, there's a probability, a 3/4 probability that the output is x1. Yeah. And a quarter probability that it is, is y1. And a 0.25 chance that it is y2, this one here. And of course, it makes sense because py is equal to x is equal to px. Yeah, these are the x's, but now I'm dealing with the px's multiplied by p y given x, which is the matrix of transitional probabilities. So you can see the y can only be so the y's will have if you multiply this, I mean the figure, this will be x1, x2, x3. So you are multiplying that with the matrix. So you can see where this is coming from. That is y1 is simply 3/4 x, yeah, isn't it? Because you are multiplying this with this. So y1 will just be 3/4 x of 1, or rather the probability of x of 1. Yeah. Yeah, so this, and y of 2 is x of a quarter of x of 1. So we are saying that this is what we call a lossless channel. Yeah. So it has got the inputs will be less than the output probabilities. Yeah. That is a lossless channel. The next channel is the deterministic channel, and this has one non-zero element in each row, and that element must be one. Yeah. So again, you can see it here. That is deterministic. So we are saying this can happen, of course, like here, because this is one, you can see there is the direct correspondence uh, of x3 and y5. It doesn't have because of this one here. Yeah. So no information is lost in transmission in a lossless channel. So deterministic, this is a channel. It has one and zero element in each row. Yeah. And that element has to be one. Yeah. Because this element has to be one. Because this value has to be one. Yeah. And this is a good example. And you can see here we have more x's than y's. Yeah. You have more outputs, input symbols than output symbols. Yeah. But again, we are saying here, if you have x1, yeah. Actually, you can see, maybe you should have started from here. You can see here, if you have x1, there's a possibility of getting y1 or y2. Yeah. But if you have y1, you know for sure x1 was sent. Yeah. You are sure that whenever you get the symbol y1, you know x1 was sent. When you get y2, you know x1 was sent. That's what it's saying here. Yeah. But in this other case, we are saying when you get y1, you don't know whether it was x1 or x2 that was sent. But when you send x1, the output will be y1 with certainty. Yeah. I think we are going to look more at the characteristics of this channel in terms of information. Yeah. In terms of the HYX, I mean H, the entropy, the transitional entropy. Yeah. Because we have the source entropy, we have the Y entropy, the output entropy, and then we also have transitional entropy. We are going to have a look at that next. So then, of course, so that is a deterministic channel, and of course there is a noiseless channel. And this one you can see the noiseless channel, m is equal to n. So they are both. So the matrix, of course, will be like something like that. To actually be the identity matrix. Yeah. In this case, this is a noiseless channel. So we normally say a noiseless channel is both lossless and deterministic. Yeah. And m is equal to n. Because once a noise is noiseless, because noise is our only source of loss of information, it becomes lossless and it also becomes deterministic. I think in the next class we are going to look at the characteristics of each of these channels in more details. I'll not include them in the notes, but I think I'll include that. And then, of course, the other type of channel is what you call the binary. symmetric channels. Now, here, when you talk of binary, now you're talking about very specific, not, you don't have x1 to xn, we have 0 and 1. That's a binary uh, channel. So a binary symmetric channel is defined as a channel given by these probabilities, where P is the probability of getting a 1 when you send a 0, or of getting a 0 when you send a 1. Yeah, that's a probability. That's a P. Yeah, and you can see we call it symmetric, because the probability of getting a 1 when you send a 0 is equal to the probability of getting a 0 when you send a 1. Yeah, because this P is the probability, kind of the error probability, the probability of getting the wrong bit. Yeah, so 1 minus P is the probability of getting the correct bit. Yeah. So the common transition is noted by P. Yeah, this is a common transition probability. It's P. So, any questions? Um, so this book, if you can download it, is good for you. Actually, it covers most of what we are going to cover, but it is the information theory where it covers best. Yeah, I use many books, but I like, for information theory, I prefer this book. Yeah, for other things, I prefer Sklar, Bernard Sklar. So, and I saw it is one of the books recommended also, I think, for 421. Yeah, so it's club, Bernard Sklar. So I'm sure you're familiar with it. Yeah. So are there any questions? I've been talking for 1.5 hours. So now I want to, and they said there's more information when you talk less. So I think we do what we normally do. Just post your registration on the chat.
Excuse me, sir.
Yes, somewhere.
Yeah, there was that example where you are showing us, I think it was compression, where we had 1 followed by 15 zeros and then 1, 1.
Yeah. Yes.
And then I kind of understood that now the zeros, instead of sending 15 zeros, they can be sent as an hex.
Well, it can be sent, it can be represented. Okay. What I meant by hex, not necessarily hex. It means you can, even in binary, because hex is just a group of bits. Yeah. So maybe I use the wrong terminology. Just send it with less bits. We are saying you can have 4 bits. Yeah, because hex. Remember, you're only sending binary, so even hex just represents binary. Yeah, I may have used the wrong word. You can send binary. Yeah. I think I withdraw that one of sending hex, because hex is just a representation, but the actual transmission is binary. So I meant you can use 4 bits instead of carrying all those zeros to indicate 15. So that's wrong, giving that example of hex. Hex is just a representation. Yeah. Remember, even when we say, when we are storing data, we normally say is we call them hex files. But really everything is stored in binary. But the hex represents, for us humans, we like dealing with the hex to represent each hex number to represent 4 bits. Yeah. Because we can remember that more easily. So I was wrong about that. especially when I talk about transmission, I should not be talking about hex. Is that okay, Samuel?
Yes, thank you.
Okay. And it's good you clarified that, because sometimes when we are talking, we might use a wrong one, then somebody answers in the exam, and then I mark you wrong, and I'm the one who sees it in class. So it's good you clarified that. So if everybody has posted on chat, let's meet next Wednesday. Have a good rest of the week and a good weekend, and see you next Wednesday.